Hello everyone. So today we're going to go over section 11.2, analyzing rational functions. So in example 1, we have y is equal to x squared minus 4x minus 12 all over x plus 2. And we will first consider the denominator x plus 2, as it will give us the non-permissible value. Since we know that x plus 2 cannot be equal to 0, we can solve for x and get x cannot be equal to negative 2. So next we will try to graph the function. First we'll factor the numerator. So we'll get, instead of x squared minus 4x minus 12, we will get x minus 6 and x plus 2 as the two factors. And of course, the denominator is still x plus 2. Notice that the factors of x plus 2 will be eliminated. And we're just left with y is equal to x minus 6. Now, what this means is that the non-permissible value will not generate a vertical asymptote, as in the previous section, but instead will be a point of discontinuity because of this common factor in the numerator and denominator. Okay. As such, the domain will be that x cannot be equal to negative 2, and to find the range, we will substitute this value of negative 2 into the simplified function, and we get negative 8. Which also, when they combined, we get the point of discontinuity, negative 2, negative 8. So if we were to graph the function, this is what we'll get. The function is simplified to x minus 6, but since x cannot be equal to negative 2, we have a point of discontinuity, which is represented by an open circle. And the coordinates of this point of discontinuity, of course, are negative 2 and negative 8. Okay, so next we have just a definition of the point of discontinuity. It's if we have a rational function, as we did in example 1, and where both the polynomials have a common factor, then the non-permissible value of the factor that gets reduced is called point of discontinuity, as we saw with negative 2 and negative 8. Sorry about that. So next we have example 2. Given what we saw in example 1, you'll be tempted to try to factor and eliminate a common factor. So we'll get x and then x plus 2 in the numerator all over x minus 2, which of course does not produce a common factor, and so there's no point of discontinuity, and the non-permissible value will instead cause a vertical asymptote of, in this case, x equals 2. I'm going to go ahead and draw that into the graph here. There we go. So, what we're going to be looking at next is what's called a slant asymptote. And we can find the slant asymptote by rewriting the function using synthetic division. So in this case, we have the coefficients 1, 2, and 0, since there's no constant in the numerator. And then 2 on the left-hand side. So now we can divide, carry the 1 down. 2 times 1 is 2. 2 plus 2 is 4. And then 2 times 4 is 8. And 0 plus 8, of course, is 8. So that will give us a quotient of x plus 4. And the remainder will be 8. Okay. And that allows us to rewrite our function as x plus 4, which is the quotient. The remainder is 8, and is still being divided by x minus 2. So it's just another way of writing a kind of division statement. So this first part is the quotient. The 8 is the remainder. And x minus 2 was the divisor, or the denominator. Okay, so we can consider what happens as the values of x gets very large. What is going to happen with this part of the function is that it will approach 0. And so we're only going to be looking at x plus 4 at that point, which means that as x gets larger, the function approaches x plus 4. Likewise, when x becomes very negatively large, again, the second part of the function, this part, becomes very close to 0, and we'll be only looking at, once again, x plus 4 as kind of what the function will become. And of course, we will have a graphical representation of that. So again, the slant asymptote is y equals x plus 4. And we find that by using synthetic division. Okay. So to sketch the graph, we will now find values of x that are close to 2, where the vertical asymptote is, and complete a kind of table of values. We'll let x equal to 1. So y is going to be equal to 1 squared plus 1 all over 1 minus 2, which of course, oh, sorry about that. This is supposed to be 2 times 1. There we go. So this will give us negative 3. So one of the points on the graph will be 1 and negative 3. And next we can let x equals to the other side of the vertical asymptote. So we're going to let x equals to 3. We have 3 squared plus 2 times 3 divided by 3 minus 2, which is 1. So y is going to be equal to 15 So another point will be 315. You could use a couple of more points, of course. So let's go 2 spaces to the left of the asymptote. You let x equal 0. And then y is going to be equal to 0. So the point 0, 0 is also on the graph. And finally, if we let x equals to 4, okay, so let's substitute in 4 here. 4 squared plus 2 times 4 divided by 4 minus 2, which gives us 12. So one of the points is going to be 4, 12. Let's go ahead and plot those here. 1. So now we can go ahead and sketch the graph with the points that we added. Knowing that the graph must approach the asymptotes at some point. And this is kind of what it could look like. Okay, let's look at another example of oblique asymptote or slant asymptote. So again, we can start by dividing. Actually, before that, x squared plus 2x minus 1, which of course is the numerator, has no common factor with the denominator of x plus 2, so the vertical asymptote is just going to be x equals to negative 2. And now we can, of course, go ahead and divide as we would. Okay, so the coefficients are 1, 2, negative 1, and then negative 2 on one side, 1, negative 2, 0, 0, and then minus 1. Okay, so the quotient is just going to be x, and the remainder is negative 1. Which means we can rewrite the function as x minus 1 over x plus 2. Okay. And that is the slant asymptote will be at y equals to x. Let's go ahead and add those in. So now, just like the previous example, we're going to let x equals the value that are close to the vertical asymptote to add additional points so we can sketch our graph. So we're going to let x equals to negative 3. So we get y is equal to negative 3 squared plus 2 times negative 3 minus 1 all over negative 3 plus 2. And so once everything is evaluated, we just get negative 2. And so one of the points is going to be negative 3, negative 2, which is right here. So now we can let x equal to -1 on the right-hand side of the asymptote. So y is going to be equal to -1 squared plus 2 times -1 minus 1 all over -1 plus 2. Oops, sorry about that. Okay, so once again, we get -2 once everything is evaluated. So a secondary point will be -1 and -2. So right here. And from there, we can just use the fact that the graph needs to approach the asymptotes. So we can draw it this way, going towards the vertical asymptote and approaching it. And then on the other side, towards the slant asymptote. And same thing on the right-hand side of the graph as well. And that's it. So one final kind of example we can look at today is a rational function that has both asymptotes and points of discontinuity. Okay. So in this case, we can factor the function, numerator and denominator. So top part we have x minus 4, x plus 2. And the denominator can be factored to x minus 1, x plus 2. Which of course will give us our non-permissible values of 1 and -2. And we have a common factor of x plus 2, which will become a point of discontinuity. But we don't know what the y-coordinate is going to be yet, so we're just going to leave it as -2, comma. The other non-permissible value of 1 is going to cause a vertical asymptote, so we can write x equals 1 under asymptotes for now. And from here, what we can do is substitute in -2 to find the point of discontinuity. Kind of like what we did in example 1. Okay, so we're going to substitute here, -2 minus 4. Sorry about that. All over -2 minus 1. Okay. Which gives us -6 over -3. Which of course is equal to 2. So the point of discontinuity has coordinates -2, 2. Okay. What about the function proper? Well, we are still left with x minus 4 over x minus 1. So here we can use, once again, division. Okay. With the numbers 1, -4, and 1 on the left-hand side. 1 times 1 is 1. -4 plus 1 is -3. So we have a quotient of just 1 and a remainder of -3. And that allows us to rewrite the function as (1 minus 3 over x minus 1. And just as before, the quotient will tell us what the horizontal or slant asymptote is. In this case, it's going to be y equals 1. So we can go ahead and add that in. Okay. And we're going to add them to the graph as well. And since we're here, we can also add in the point of discontinuity of negative 2, 2. And from there, just like before, we can now find some points around the vertical asymptotes. Sorry, the vertical asymptote, we only have one. Again, by substitution. So we're going to let x equal to 0. And of course, that would just be y is equal to 0 minus 4 divided by 0 minus 1. Which is going to be 4. So one of the points is going to be 0, 4. Next, we can let x equal to 2. So we have 2 minus 4 all over 2 minus 1, which is going to be negative 2. So another point is going to be 2, negative 2 here. And we're going to add in one more point. We're going to let x equal to 4. And the reason for that is because 4 minus 4 in the numerator will give us 0. So that's an easy point to add in. So we have also 4, 0 on the graph. So now we can go ahead and sketch the rest of the graph, knowing that it must approach the asymptotes. So we have something that looks like this. Okay. And finally, the domain and range. The domain, of course, x cannot be equal to negative 2 for the point of discontinuity, and also 1 for the asymptote. The range, y cannot be equal to 2, again for the point of discontinuity, and also 1 for the asymptote. So that's it. We looked at how to find oblique or slant asymptotes, and we also looked at how common factors can cause points of discontinuity. And so that's it for today. Once again, thank you for listening.